One of the tools that we'll need to make the connection between the area under a curve and integration is summation notation, which I usually call sigma notation. Sigma notation is a way to represent the sum of a sequence. You might recall that the items in a sequence are given an index. Typically, the first term is A1, the second term is A2, that's supposed to be a 2, third term is A3, and so on. Like for loops in computer programming, we use an index variable to keep track of which item in the sequence we are referring to. Our index variable is typically k, and the term of the sequence would be a sub k. And eventually we get to the last term, which is typically a sub n. So one sequence might be 1, 3, 5, 7, and 9, where 1 is A1, 3 is A2, 5 is A3, 7 is A4, and 9 is A5. In this sequence there are 5 items, so we would say n equals 5. That's the number of items. And if we wanted to generalize the value of each term in this sequence, since it's just the odd numbers, we could actually say that a sub k is really just 2k minus 1. So when you plug a 1 in for k, a sub 1, we get 2 minus 1, which we know is 1. A sub 2 would be 2 times 2, which is 4, minus 1, which is 3, and so on. Now, if you want to add the terms of this sequence up, because we know there are only 5 terms, we can just write out that sum as 1 plus 3 plus 5 plus 7 plus 9. And we also can use sigma notation to represent this sum. Let me show you what I mean. You can see here in the diagram that we're showing you the parts of sigma notation. The summation symbol, which is that big E looking thing in the middle, that's called sigma. That's a Greek letter. And what we do is we represent the terms of the sequence with an expression here, a sub k, and we say we want to add them up by using the summation symbol, which is the sigma. And then you'll notice that we have a couple of extra pieces of information. Our index variable, k, is given a starting value. And that information is written underneath the sigma. Then above the sigma, we are given the ending value, which is denoted by the letter n. So if we wanted to write out the sigma notation for that sum 1 plus 3 plus 5 plus 7 plus 9 that we just had on the last slide, we would put a sigma. We would say that k is starting at 1, because we had a sub 1 is our first term, and ending at 5, because a sub 5 is our last term. And then we would write the formula that we showed, 2k minus 1, to represent the value of a sub k. And so the way this notation works is we simply start counting at 1, and we plug that 1 in for k, and we get 2 times 1, which is 2, minus 1, which is 1. Then we put a plus sign to separate the terms. And then now that we used 1, we start counting up until we get to 5. So now we're going to use the value of 2. 2 times 2 is 4, minus 1 is 3. So we write that piece down, that sum down, that value down. Then we put a plus sign. Now we've taken care of 2, so now k is 3. We plug that in, that's 6 minus 1, which is 5. And we repeat that for 4 and 5, and we get 7 and 9. The value of this sum then is the value you get when you add these numbers up. Let's see if I can get this math right. 10 15 plus 10, it's going to be 25, right? 10. Yes, I did that right. Okay, so that's kind of how the sigma thing works. Let's take a look at a few more examples. So when we're evaluating the sums for these sums that are written in sigma notation, we go through the same process that we just went through for that sequence of 1, 3, 5, 7, and 9. Let's say you're given the sigma summation from 1 to 5 of letter K. So we simply start counting with K equals 1. And there's no math to do, it's just K equals 1, so we write down the 1. Cross that out, the next time it's a 2. That's supposed to be 2. Plug the 2 in, there's no math to do, so we get a 2. Cross that out, it's a 3. Cross that out, it's a 4. And we stop when we get to this top value 5. So there are the 5 terms of the sequence. Now we're going to add these up. So 1 plus 2 plus 3 plus 4 plus 5, that answer, that sum is 15. And that would be the value of the original summation notation. Let's try another one. How about the sum as K goes from 1 to 3 of negative 1 raised to the K power times K? Well, when we do this summation, the first time through K is 1. Negative 1 to the first power is negative 1 times 1, which is negative 1. Then the next time, this is a 2. Negative 1 squared is positive 1 times 2, which is 2. Then the next time we're at value 3. Negative 1 to the third is negative 1 times 3, so that'd be plus negative 3. So this whole value here has a sum of negative 2. And that would be the value for that sigma notation. Let's do one more. What about K is from, let's go 1 to 2. Just that'll make this a little shorter. And let's do K over K plus 1. So as we're evaluating this sigma sum, we're going to start by plugging 1 in for K. That would be a 1 plus 1 over 1. 1 over 1 plus 1, I should say. And then the next time through, K is 2, which is the last value. That'd be 2 over 2 plus 1. And when we simplify this, that's 1 over 2 plus 2 over 3. Get a common denominator. That's going to be 4, 6 plus 3, 6, which is 7/6. And that would be the value of that sum. So the process of computing these sums, as long as the value of n is relatively small, is simply the process of using substitution through each term of the sequence, then adding up those values. Now, just like the other tools that we've used in calculus, limits, derivatives, indefinite integrals, once we have the structure in place for our tool, we find out that there are properties and rules that we can use to more efficiently work with this structure. So we know now that we have this structure K equals 1 to n of a sub k, and just like our other tools, these 4 rules are true for sigma notations as well. We have a sum rule. So if you're doing a sigma on a sum, you can break that into the sigma of the first term plus the sigma of the second term. Same thing with differences. You can do it with the minus sign. If there is a constant factor or a constant multiple in each of the terms, you can factor that out, calculate the sum, and then just multiply the answer. And finally, if your sigma expression has a constant number, then the value of that summation is just n times c. Let me give you a quick little for instance here. Let's say it was the sum of k equals 1 to 10 of the value 7. all this really is 7 added 10 times, which we know is 10 times 7, and so we just write 70. Okay, that's what this last rule means. So what we'll do is we'll practice using these rules to help us evaluate some more complicated summation problems. So let's evaluate this sum. We'll go k equals 1 to 3 of 3 minus 2, let's do 2/3 k. Okay, so we have these rules. First rule is the subtraction rule. We can break this into two sums, and that'll make the answer for this one pretty easy. And the other thing we'll do is we'll factor out the 2/3, because that's a constant multiple, and we'll just have k there. Now, right here we have a constant summation where our value is 3, our constant is 3, and we're going to k from 1 to 3, so this is just 3 times 3, which is 9. So this one here is 9. And then here what we're going to do is we're going to add up 1, 2, and 3, which is 6, and we'll multiply that by 2/3. So what we're going to be subtracting is 2/3 times 6, which is 4. So the value of that one's 4, and so this entire sum is just 5. Just a more efficient way to compute that, rather than plugging the 1 in and subtracting from 3 each time. We break this into pieces and we can quickly get to that sum. Okay, now let's skip ahead to the pieces we really need. When that value for n is small, let's say less than 10, and it's known, these summations are pretty straightforward. You're just going to plug in numbers and add things up. But as the value of n either becomes unknown or grows larger without bound, adding these sums up by hand becomes impractical. So what we want to do is develop some formulas for computing these sums quickly without having to list out all the terms in the sequence. For example, let's start with something that sounds pretty simple, which is finding the sum of the first n integers. And in summation notation, we write that like this. We say k is going to go from 1 to n. Notice we are not giving you a value for n. We're just saying that it is the letter n. And then the expression for each term is just k. Now, until we know what the value of n is, we can't really even write the value of the sum. What we can do is write out what it would look like. And apparently I made a mistake here with my pen. Alright, let's do this. Here we go. So, when k is 1, then the value of k is just 1. When k is 2, the value of k is just 2. And this goes on for a while, right? Eventually we get tired of writing these things. And so I'm going to put these 3 dots, the ellipses there, to represent that I'm listing a bunch of numbers with plus signs in between them. And eventually I can get to the end of this list. The end of this list is the second to the last value we can say is like n minus 1, and then the last one is n, right? So although I can't get to the end of this list because I don't know what the value of n is, I can write out approximately what it looks like. 1 plus 2 plus 3 plus ... plus n minus 1 plus n. Okay, so I know that the answer to, or the value of, this summation is whatever the answer to 1 plus 2 plus 3 plus 4 all the way to n is. Okay. Well, this isn't really a formula. It doesn't help me. It doesn't help me because these 3 dots are a mystery, and we can't deal with a mystery. So I'm going to do something different. Let's write this notation out in a little bit different way. Okay, so here it is. I'm still going to write the same thing over here. Right? This is the thing we're trying to find. But since I know that addition's commutative, can't I just reverse this list? So isn't the sum of the first n integers the same as adding them backwards? So the first one would be n, the next one would be n minus 1, the next one would be n minus 2, and so on, all the way down to 3 and 2 and 1. So I'm just listing this thing backwards. Now remember, these are the terms here, right? And so this is another way to write out the value of this sum. Now check this out. What I'm going to do is I'm just going to add these things straight down, just like you would in an elementary arithmetic class, column arithmetic. When I add these two sigmas together, they are the same thing, so that just makes 2 of the sigmas, right? There's one on top and one on bottom. When you add them together, you get 2 of them. So I get 2 of these sums. Sigma as k goes to 1n of k. And then over here, I can add each of the terms, right? In the columns, I can add these 2, and I can add these 2, and I can add these 2, and I can go dot, 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 and I can add these 2 go together. Here, I don't have one for 3. That would be n minus 2, and then I have this 1. So check out what happens. 1 plus n is just n plus 1, or 1 plus n, but I'm going to write n plus 1. And then 2 plus n minus 1 is also just n plus 1. And 3 plus n minus 2 is also n plus 1. And then guess what's going to go on in the middle here? Those guys are all n plus 1. And we get to the end and we have n minus 1 plus 2, which is n plus 1. And we have n plus 1, which is n plus 1. Okay, so by adding these two sequences together, each corresponding term when added together has a value of n plus 1. Turns out there are n of these things. There are n of them. So rather than writing out n plus 1 plus n plus 1 plus n plus 1 with the 3 dots in there and then some more n plus 1s, I can simplify this to n times n plus 1. And that n times n plus 1 is the answer for 2 times the summation that we were looking for. So I hope you can see that if we want to solve for just the summation, we simply divide by 2. Okay? And that's not fitting on my screen there. That was a ridiculous attempt, in fact. So let's not put that here. Let's wrap this up on the next slide, and I'll show you the formal wrap up to this particular derivation. Okay, so here it is, typed out nicely. You don't have to worry about my handwriting. It turns out that the formula for the sum of the first n integers is just that n times n plus 1 divided by 2. And we're going to use this a lot in the problems that we're going to be working on. And this is going to be also very helpful in making that connection from the Reimann sums, right, the area that we were estimating, to our definite integrals, which we haven't discussed yet. So this formula was developed through that process that I just showed you on the last slide. For the other two formulas that we're going to use, I'm just going to let you know that somebody else already went through the process of deriving those, and we are going to reap the benefits of their work. So this guy right here, this is a big one. Make sure you have this in your notes, that when you're adding up the first n integers, it's n times n plus 1 over 2. And then I also want to give you the sum of the squares, and the sum of the first n squares, and the sum of the first n cubes, and I'll do that on the next slide. So here they are as promised. If you ever need to add up the sum of the first n squares, right, if you ever see this in one of our problems, you are going to automatically convert it to this. You're taking a summation notation and converting it into some algebra. Same thing with the cubes. Okay? And I'm not going to go through the process for deriving those. It's a longer discussion, and this video is already way too long. But take it from me and from your textbook. These formulas are, in fact, valid. Let me show you briefly, with a couple of quick examples, how we can use these formulas to make our work a little faster. Okay, to wrap this one up, let me run through a quick little solution to this particular problem here. So we need to add this thing up. I could plug them in each time and eventually crank out the value. But just by using our rules that we've developed, along with a couple of these formulas, or one of these formulas, we can quickly get the value of this thing. So I'm going to use the sum and difference rule along with the constant multiple rule to break this up into 3 sigmas. The first one is k equals 1 to 6 of k squared. And we just showed you a formula that we'll use to evaluate that particular sum. The next one is a minus a 2 times the sum of k equals 1 to 6 of just k. And I derived that particular formula for you. And the last one is the constant 1. Okay, so let's run through our formulas. Well, the formula for the sum of the first n squares, in this case the first 6 squares, is n times n plus 1 times 2n plus 1 over 6. So for us, n is 6. Can I write? Yes, I can. So there's our n. So our thing is going to be 6. Oh goodness, I'm not writing very well. 6 plus times 6 plus 1, which is 7, times 2 times 6 plus 1, which is 13, divided by 6. That's for the squares. Then we've got a minus sign, and we're going to do 2 times the sum of the first 6 integers, right? And we have a formula for that. That's n times n plus 1 over 2. So that's going to be 6 times 7 over 2. And then on the end here, we're going to add on the formula for the constant rule, which is just 6 times 1. So that's going to be plus 6. Okay, and then so to get this value, we can simplify this a little bit. These 6's are gone, these 2's are gone, and this is going to be 7 times 13 minus 6 times 7 is 42 plus 6. And so this is 91 minus 42 plus 6, which is 55. So 55 is the value of this sum right here that we wrote. And we used our formulas and our rules to quickly compute that sum. So that's sigma notation. We're going to practice a few of these just to play with it, and then the next thing we'll do is show you how these help us with the areas that we've been estimating. Take care.